night sky is packed with stars. In our galaxy alone, there are over 100 billion stars, and in fact there are over 100 billion galaxies in our observable universe. There are more stars than there are specks of sand on Earth. Every star is powerful, creating the basic matter for everything in the universe, including us. Most are so far away we know little about them. But there is one star that is really close, and virtually everything we know about stars we've learned from that neighbor. Our sun is a blinding ball of light, but take away the glare, and one of the most powerful objects in the universe appears in our own backyard. It's a ball of superheated gas that's been lighting our solar system for 4.6 billion years and dominates all life on Earth. It's nearly 1 million miles in diameter, yet our sun is tiny compared to the really big stars out there. Eta Carinae, over 5 million times larger than our sun. Betelgeuse, 300 times larger than Eta Carinae. And then there's this monster, VY Canis Majoris, the largest star ever discovered, 1 billion times bigger than our sun. Each star is a one-of-a-kind, but they all start life in the same way, as clouds of dust and gas called nebulas. Many billions of miles across, they drift through space, forming spectacular shapes. Each nebula is a star nursery, where millions of new stars are being born. But this birth is hidden from view.
Some of the more darker parts of the nebula are the most dramatic parts and forms of star formation. That's really where the stars begin life.
The dust clouds are so thick, regular telescopes can't see inside.
There's nothing more important to us than the formation of stars, and until just recently, we could not observe the more darker, denser part of the nebula, which is where stars form. Not until 2004, when NASA launched the Spitzer Space Telescope, is when we could first observe star formation. This telescope was an infrared telescope, so it showed us exactly where all the heat was coming out of the dark, more dense areas of the nebula.
Heat passes through the thick dust of the nebulas, allowing Spitzer to see new stars coming to life. These remarkable pictures capture the earliest moments of a star's life, as pockets of hydrogen gas begin to heat up. All you really need to make a star is gravity, hydrogen, and time. That's all you need. Gravity pulls the dust and gas into a giant swirling vortex. Over hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk, bigger than our entire solar system. Gravity brings matter together, and when you squeeze matter into a small space, it heats up. It's a simple law of chemistry. At its center, gravity crushes the gas into a giant, superheated, super-dense ball. Pressure builds until huge jets of gas burst out from the center. So it really shows you how violent of a process star formation can be. It's literally taking matter and accelerating it over massive distances, light years across. Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the star gets smaller, hotter, and brighter. Temperatures at its core reach 15 million degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born. It will shine for millions, even billions, or perhaps even trillions of years.
A star is a giant hydrogen bomb. So why doesn't it just explode? Gravity is the answer to that. Gravity is compressing the outer side of the star. Gravity and fusion. Gravity wants to crush the star into smithereens, but fusion wants to explode the star, so they cancel out.
Fusion, at the core of a star, generates the explosive force of 1 billion nuclear bombs every second. When the sun fuses hydrogen and helium into its core, it creates a particle of light, a photon of light. Each beam of starlight makes an epic journey. Light travels at 670 million miles an hour. A beam of light can travel around the Earth 7 times in 1 second. Nothing in the universe moves faster. Yet most stars are so far away. Their light takes hundreds, thousands, millions, even billions of years to reach us. So when the Hubble Space Telescope looks into the far corners of our universe, it sees light that's been traveling for billions of years. But even before light starts its journey through space, it's already been traveling for thousands of years. It doesn't get very far before it immediately slams into another particle, another neutron, another proton. Once these particles are created, they're immediately bouncing off of other particles inside the star, and it has to work its way out of the star. So it takes thousands of millions of years for the particles to even get out of the star. And once it's out of the star, it takes only about 8 minutes for that light to reach us on Earth. For the photons, it's a wild ride, smashing into atoms of gas billions of times as they struggle to escape from inside the star. From the moment of its birth, every star is destined to die. Its fuel will run out. Then gravity will win the battle with fusion, triggering a chain of events that will destroy the star. Our sun is no exception. Every second, it burns through 600 million tons of the hydrogen fuel at its core, and at that rate, the hydrogen will run out in about 7 billion years. As the hydrogen gets used up, it slows down the fusion of the star's core. This gives gravity the edge. With less fusion pushing outward, gravity crushes the star in on itself, but fusion fights back, heating the star's outer layers. As the sun heats up, it'll swell from about 1 million miles up to 100 million miles across. Our sun will become a red giant. Temperatures here on Earth will reach thousands of degrees. Then, the bloated star will engulf the Earth. But the giant red star is self-destructing. Its core becomes dangerously unstable. With no hydrogen left to fuel it, the star begins burning helium and fusing it into carbon. The star is now destroying itself from the inside out, blasting violent surges of heat from its core to its surface. These energy waves blow away the star's outer layers. Slowly, it disintegrates. The star is dead. All that remains is an intensely hot, dense core. The red giant has become a white dwarf. Our sun will end its life as a white dwarf, about the size of the Earth, but 1 million times denser. At the heart of a white dwarf, astronomers believe is a giant crystal of pure carbon, a cosmic diamond, thousands of miles across. But stars can create something much more precious than a massive diamond. When stars much bigger than our own die, their death is much more violent. But in dying, they create the building blocks of life. Less than 600 light-years from Earth, the monster star Betelgeuse is near death, in space years. It's younger than our Sun, millions, not billions of years old, but the fusion at its core is far more intense. Betelgeuse is a different beast from the Sun entirely. It's a red supergiant. The reason is because Betelgeuse is more massive. It has 20 times the mass of the Sun, and that means what's going on in its core is very different than what's going on in the Sun's. The gravity of stars as large as Betelgeuse is so powerful it can smash together bigger and bigger atoms. The core of a massive star is a kind of factory, manufacturing heavier and heavier elements, which is also what leads to the star's destruction. Once it makes the element iron, the star is doomed.
In the world of science fiction, there are hundreds and thousands of ways of ideas on how to kill a star. Really, killing a star is as simple as iron. Iron is like a poison to a star. Once a star starts to make iron, it has written its death sentence. The iron that the star makes, it's inside the star. As the star tries to heat up the iron, but it can't because it's absorbing the heat. So the sun is basically killing itself.
Iron absorbs energy. From the moment a giant star creates iron, it has only seconds to live. The battle between gravity, trying to crush the star, and fusion, trying to blow it apart, is over. With iron, fusion hits a dead end. Gravity always wins. The iron core collapses. The outer layers of the star slam into it, and a huge explosion is generated. It's the single most violent event in the universe. A supernova.
After a supernova, science used to think that there was nothing left. When actually left, there was a giant amount of matter left known as a neutron star.
The super-dense core is now a neutron star. It's around 20 miles across, and unbelievably heavy. It's incredibly dense. Just a cubic centimeter, the size of a sugar cube, of neutron star material would weigh as much as all the cars in the United States of America combined. The dying star doesn't just leave the corpse of a neutron star. It blasts the new elements far out into space. These clouds contain the building blocks of the universe. Everything we know and love is built from this stardust. This stardust is full of elements, like hydrogen, carbon, oxygen, silicon, and iron. The raw materials to build new stars, solar systems, planets, and of course, us. Everything we see around us once blasted out from the core of a star. Even the atoms in our own sun are recycled. They're third or fourth generation. They're leftover debris shot into space from dying stars long ago. We live in an age of stars, but it will come to an end. There's only so much hydrogen in the universe. Trillions of years from now, it will all be used up. And when there's no hydrogen left, there will be no new stars. We live in a very brief period in the history of the universe. While we still have stars illuminating the sky, stars creating life as we know it, but it's not going to last forever. Sooner or later, the stars will begin to blink out. First, the massive stars will burn out. Then, mid-sized stars like our Sun, leaving only the smallest. Trillions of years later, they too will fade away. Slowly, inexorably, the universe will get colder and darker, until the last star burns out and the universe becomes dark once again. The age of stars will be over. But right now, we are in the golden age of the universe. This is the best time to be alive. This is the time when life can flourish, stars can form. We live in the stage where stars glow and illuminate the night sky, when stars create life as we know it. We live in the best of all stages of the universe. For now, stars will continue to shape our universe, generating the building blocks of new worlds, creating new stars, and filling the darkness with light.